All right, so now I need to introduce a magnet to it. We have magnets for this very purpose. Now, I know which side is north and which side is south because it is labeled. I'm trusting the manufacturer. The north end is over here. This is the north end. Now, look what's happening to the iron filings. They are starting to move. Now, it doesn't tell you what is the north side and the south side. Oh, what the heck. Let's see. But you can see that the iron filings are sort of lined up, and you can see that there does seem to be some sort of structure happening along here. So the North Pole was down here, I believe. So the north end comes here, around into the south end over there. I have a second magnet. I'm going to stick it in here. And so this is sort of a reality here. We still have the north end down here, so the north end, the magnetic field lines are coming like here, up and around. But you can see at the junction, you also have some north and south poles here. It's not an ideal magnet where you just break it apart and put it back together again. There is a difference between two magnets stuck together and two that are not.
So most of it is still going to the ends?
Yeah, I would say that, but you do have some build up here. So, evidence that there is something that exists that is going from one pole to the other.
Why is it that like when they're split, they're not the same as if they were just coming together? Like even if they're like the same length, same weight. I don't know what accounts for that.
I suspect that happens is that in our nice ideal model of a magnet, with the north end and south end, we assume the magnetic field lines go like that, but and then out the ends. But really, the manufacturing process is not so ideal that the magnetic field's coming out at the very end. There's stuff coming off, near the tip on the sides. That's where the issue comes in. All right. Other questions up to here? All right, let's take a look at a slightly different view. And focus. All right, so these are just little bits of iron. Trying to sort of get them in some sort of random order there. And this one should be much closer or much faster. And you can see automatically, just for trivia, this is the north end down here. But you can see the little iron bars starting to having changed direction. The ones that are farther away, less impacted. And then, if I take our most powerful magnet, which is right here. Now, it'd be nice to take these out of the container and just have four stuck together like that, but these are a dickens to pull apart, and so we'll settle for as it is right here. And you can see the magnets are smaller, but this was tilted over there. This does tilt that way. Some of them not really affected a whole lot. We can shake it up, maybe some more stuff a little bit. Oh, that one just doesn't want to move down there. There we go. And we can then, I hadn't tried this one before, so what are the chances? Probably should not do this with this magnet in my hand. And you get sort of a quick look at the lines here. And I don't know which is the north end, which is, oh, I can find out. I take this north end. So the north end is over here. So magnetic field lines coming out of there, across the ceiling, and then around here, and you can see that these are starting to reorient towards the south. So again, evidence that there's something there, not specific about what it is, but it's something that we call magnetic fields. All right, questions? All right. Oh, sorry, Dan.
I missed when you said, but how does the field go? How does the field go on the inside of the magnet? Because I can't tell the arrows.
Oh, it goes out the north end and into the south end.
Okay.
So the way I have it here is it's going out there and then coming in here.
Basically completes the circuit.
Yeah.
Oh.
Was that it?
Yeah.
Okay. Now the fact that it completes the circuit actually is an important bit. Oh, sorry.
So the the magnetic field lines split the magnet in half lengthwise, sort of, as well. If that makes sense.
You mean,
Because it's going either direction, right? From north to south.
right.
So it's split in half lengthwise.
There should be, unless there's something else going on, there's a symmetry
Yeah.
there. Is that what
So
you were talking about?
Why is there a symmetry though? Like, why isn't it just one way instead of both?
I know that because I can take a magnometer or something to find some indication of a magnet. And if I have my magnet here, a north and south, I know that there's a magnetic field at this spot. I can do a measurement and I see that it's going that way. I know I have a magnetic field here too, and a magnetic field here, and a magnetic field here. I can get magnetic fields at different spots, and that's generally why you draw it with more than one line.
Okay.
Same with electric field. That answer? Okay. Other questions before I just zip on? All right, let's talk about units. Oh, that's right, the other thing I was about to talk about. Gauss's law of electricity said the integral E dot dA is equal to the enclosed charge over epsilon. So Gauss's law of electricity, this was basically Coulomb's law falsified. But we have it equal to this enclosed charge because I can have just a positive charge or a negative charge. However, with magnets, I do not have that. No matter where I draw any type of surface, I have just as many lines going in as I have going out. So we have Gauss's law of magnetism, and that if I take the magnetic flux through any surface, that is equal to 0. This is what all this is saying is that every magnet has a north pole and a south pole. I cannot have just a north pole or just a south pole. Which doesn't stop theorists from going, yeah, we haven't found the magnetic monopole yet, but that's not saying it doesn't exist. If we find it, here's the set of equations. And so there is a set of equations if they ever find it. They're raring to go. They have this thing called magnetic charge symbolized by a lowercase m, at least the one that I saw, the version I saw. That is well beyond the scope of this course. Matter of fact, it's beyond the scope of most physicists because they haven't found the magnetic monopole yet. but just in case. These are two of Maxwell's equations. There were four Maxwell's equations. We've now done half of them. Units. The SI unit is the Tesla, symbolized by a capital T. Named after the person, not the car. If you go far enough, the other unit for magnetic field that you will often see is the Gauss, named after. Anyone want to take a shot at it?
George Fox.
Man, so close. Yeah, it was named after me, they just couldn't spell.
No, we were talking about the university.
Say it again?
We were talking about the university.
Ah, okay. There is a direct relationship between the two. Tesla, ultimately, the most powerful magnet, I believe, is somewhere around 27 Tesla. So it comes from other units. It's a derived unit based on stuff that we've already seen. It just sort of naturally falls out of it. It's not necessarily useful in terms of what you're working in. So Gauss, you often see more often. Just like with density, yeah, the SI unit for density is kilograms per cubic meter. However, most people dealing with density work in grams per cubic centimeter. So you'll see both. The relationship between the two is that 10 to the 4th Gauss is equal to 1 Tesla. Just double check that, make sure. Yeah.
So is there no symbol for Gauss?
Oh, I have it as a capital G. Although it might be GA elsewhere. Just not something I dealt with a whole lot.
What's the subscript right there? The
CGS. The other metric system that's based in centimeters, grams, and seconds, as opposed to SI, which is kilograms, meters, and seconds. So if I take a compass, usually there's an arrow there. Assume at some point everybody has seen a compass, not the compass with the 2 sharp points in the pencil, or the pencil and the sharp point. I'm talking the one for magnetic fields.
The one that points north?
North end and south end. What was that?
The one that points north.
Yeah, it points north. This is actually the north end of the magnet, right there. And it points north. So what does that tell you about the magnetic field at the North Pole?
The south. That's the south?
It is indeed a south. So if you look at the Earth, magnetically speaking, this is the North Pole, which is a magnetic South Pole. So you have the geographic and you have the magnetic, as well as there is the magnetic South Pole is not necessarily at the same place where basically the axis upon which the Earth rotates at the North Pole matters. They're a little bit off of one another. And at some point, the South Pole was down, the magnetic South Pole was here and the magnetic North Pole was here. It does flip. And we'll talk about what creates it. It's already been hinted at or told what creates a magnetic field, and we'll get into that in a little bit more detail. All right, and in terms of units, the Gauss The Earth's magnetic field, so D Earth, is about a half of the Gauss. As with a lot of unit systems, it's based upon something that's a little bit somewhat easy to translate. An Earth's magnetic field was a natural magnet, so why not have a unit system based on that? Oh, I was about to do my, I know what you're thinking, where's the math? And we're about to do math. I have to wait for 2 weeks.
So what's the most powerful magnet on Earth?
Actually, I'm pretty sure it is around, superconducting magnets can get up to about 30 Tesla. In a lab, typical lab magnet, 2.5 Tesla. The big magnets probably are going to be in the multi-million-dollar experiments.
Is it the particle accelerator magnet?
I suspect that's where my initial thought goes, is to that. I don't know for sure if that's the one, but
Is the one in Geneva?
that or I think that one's the bigger one. U.S. site is Fermilab outside Chicago. That would be probably our best bet for the largest one.
There's one in where too?
Geneva. I've been there. That's so cool.
Oh, you've been to CERN?
Yeah, I went to Geneva.
Oh, Nerd Central. That's probably awesome.
Don't they use magnets in like the nuclear fusion experiment for the plasma?
I believe they're used somehow. I don't know for sure how they're used at that. I believe you are right.
Yeah, 'cause I think that's how they try to keep the plasma shaped or away from the wall.
Okay, so this would be for the fusion reactor, not the fusion bombs.
Right.
Okay, my mind immediately went to
The
weapons.
fusion reactor. I saw a YouTube video where like this guy had a magnet set up to melt some metal. It was like very light metal,
Right.
like nickel or something. But it's just, it took a while, but it eventually started to melt it.
Ah,
So would that be like electromagnets that would do that? Because it would have to, the magnetic field would have to go around, right?
I would assume, let's see, to melt it, you basically want the particles to start moving faster and faster. So if I just took a regular magnet and stuck it near a magnetic material, it would realign everything, but I don't think it would excite them. So you would have to have it oscillating back and forth. And to have control over that electromagnet would make sense because you can, AC current, you're switching back and forth there. And so if you can get that frequency to match the natural frequency of the atoms, I mean,
Okay.
similar in general concept of microwaves where you shoot radiation that is at the same frequency, at the natural frequency of water. And so you hit the water and it starts to vibrate more and more.
Gotcha.
So I think it'd be something along those lines. But
Interesting.
if you find the videos like that, please send me links.
Okay.
I'd love to see them.
Cool. Have a good night.
Yep, you too.